Okay, we're recording here. So yeah, we finished up chapter 8 last time on motor system action. And now we're moving into a fun chapter, I think, on memory. Mostly today we'll be talking about the cognitive aspects of memory. So a little refresher on some of this basic cognitive aspects of memory. And then next time is when we'll start getting to some of the brain stuff as it pertains to the cognitive things that we're going to talk about today. So here's the kind of the typical, this is the kind of the classical model of memory, dividing it up into these three components. I have two different figures here. So they're both basically saying the same thing. They're taken from, this one's taken from a textbook, this one's taken from the internet. And the thing that these two things have in common, these two different diagrams, is that they both basically divide up memory into these same three components: sensory memory, short-term memory, and long-term memory. Same thing down here. The primary distinction, theoretically, between these three different types of memory is the amount of time the information can be stored in each. By definition, sensory memory, this is basically thought to be when information enters your senses. Usually sensory memory is studied with respect to the sense of vision or the sense of hearing. Sensory memory is the store where that information is maintained very briefly. And we'll talk about the specific amount of time that this information and sensory memory is thought to be maintained. In general, real quick, the sensory memory and the visual system is thought to be maintained for a very short amount of time, whereas an auditory system, it's still maintained in sensory memory for a short amount of time, but it is a little bit longer, apparently, than information stored in visual sensory memory. So auditory sensory memory seems to have a little bit longer decay time than visual sensory memory, but both are short relative to these other components. Short-term memory here has relatively longer storage time, but short-term memory has another component which is unique. So the reason I added the second diagram, because this is a diagram from the cognitive psychology textbook, which is oftentimes used here at KU, and the diagram there doesn't have this little thing right here, this like kind of self-pointing arrow that comes out of short-term memory and points back into it. And then right next to it, I don't know if you can read it, if it's a little bit fuzzy, looks a little bit fuzzy here. The word rehearsal is right there. So short-term memory is oftentimes the aspect of memory where you might, for instance, like a telephone number that you're trying to remember. Someone tells you a telephone number and you don't have your phone to type in the number real quick, so you have to remember that number. One way that you might do that is by rehearsing that number to yourself over and over. That is, you might physically say the number out loud. You might actually verbalize it. Or if you can't verbalize it for whatever reason, you might at least kind of recycle that telephone number in your head over and over and over again as a way of maintaining that information in short-term memory. So short-term memory has an interesting property. Things can be stored in short-term memory for several seconds, but if you use rehearsal, and rehearsal is thought to rely on particularly those frontal lobe parts of the brain that are important for attention. If you can kind of recycle that information by continually paying attention, playing it over and over in your head again, you can actually maintain that information longer than it otherwise would. So those short-term memory has this important property that you can use your attention, you can use your frontal lobe to help keep things in short-term memory for longer than they would be if you weren't paying attention to them, if you weren't rehearsing them, if you weren't recycling them in your head. And short-term memory, once again, is something which is thought to exist in the auditory system, and there's thought to be a short-term memory for the visual system as well. And then finally is the long-term store. So this is information that can be stored for a very, very long amount of time. So, I have memories of my childhood, the dog who lived next door to us when I was 4 years old back in Indianapolis. That was Toby. I remember, it's kind of sad actually, but the memory that came to my when was when Toby was getting old and he started having spine problems. And I remember how he kind of would walk around funny. He'd kind of have to drag. It's sad because he died shortly after this. But I remember he'd kind of have to drag his booty around. So I remember all that stuff. Those are memories that I have. And I'm getting kind of old. My birthday was just Tuesday, and that was 35 years ago or so. And I still remember all this stuff. So it's clearly those memories, those kind of images I have are in my long-term memory, about Toby is what I'm talking about today. I also remember my telephone number from when I was from all those years ago, even though I haven't dialed that number in years and years and years. I still remember my telephone number from when I was a kid at that old house in Indianapolis. Obviously, long-term memories then can be stored for up to years. And in theory, they can be basically stored your entire life. Though there's a little bit of evidence that at the end of your life, your ability to retrieve some of those memories does get a little bit less efficient. So you do kind of lose some of the ability to access those memories as you get older and your mind stops working quite as well. One last thing to say about this diagram is these bidirectional arrows that occur right here. This is the idea that, well, this arrow, which they call transfer here in this diagram, is the idea that if information is stored in short-term memory, eventually it can be transferred to long-term memory, which is not a difficult concept. I think that idea makes sense. If you keep information maintained in short-term memory long enough, then eventually it'll be strong enough that it'll be stored in long-term memory, in which case you'll be able to retrieve that information later on in your life, days down the road, or maybe even months down the road, years down the road. But retrieval is another important aspect. This arrow, which is going back to short-term memory. This is the idea that usually I'm not thinking about that telephone number from when I was a kid, 253-3058. Usually I haven't dialed that in years. Really, the only time I ever think about that number is when I'm giving lectures on memory, because I oftentimes use that as the example of memory, of a long-term memory from a long time ago. Usually that memory is stored in my long-term memory in kind of like a dormant state. I'm not consciously thinking about it. But when I decide to retrieve that memory, as I usually do when I am teaching lectures on memory, in theory, what I'm doing is I'm reaching into my long-term memory and I'm pulling it into my short-term memory. And a lot of theories regarding these different memory components assume or suggest that when you are conscious of something, some type of sensory thing in the environment that you are conscious of, I'm looking at my Star Wars mug right there, I'm looking at my pack of gum right there. When you are conscious of different things that you're looking at or hearing, the idea is that information is being stored in short-term memory. So you can take something that's in long-term memory, like, seeing Toby kind of the way he was walking at the end of his life a little bit weird, or that telephone number that I, from my childhood. I can take that information stored in long-term memory, but I can bring it into my short-term memory, and I can kind of picture it in my mind's eye, like seeing Toby, or I can hear the telephone number in my mind's ear, so to speak. And when I'm doing that, I'm using my short-term memory to kind of be conscious of these things that occurred years and years ago. So that's kind of a basic cognitive introduction to these three different memory stores. So now, actually, I guess, yeah, we are going to talk a little bit about the brain today. As I said, mostly today will be cognitive stuff, but there will be some brain stuff pertaining to auditory echoic memory that's in the textbook as well. So we're going to kind of focus in here now on each of these different three sensory components. We'll talk about sensory memory, short-term memory, and long-term memory. We'll talk about each of those throughout the course of this chapter. In my opinion, the most interesting stuff in this chapter concerns long-term memory, which we'll get to towards the end of the chapter. So talking about sensory memory, the key kind of feature of sensory memory is that once information enters sensory memory, so I talked about the main ways these have been studied with respect to vision and audition. And the idea is that information enters the sensory receptor, either your eyes or your ears, and that there's this kind of brief period of time where that information is kind of maintained in your mind, or in your body. In your mind, I guess is probably the more appropriate word, even without any type of conscious awareness of that information, or even without attention being paid to that information. It's just a sensory trace or a sensory signal that occurs. It's very brief, and it does so before any type of cognitive processing can occur. I kind of think of this sensory memory as basically like those parts of the body and the mind that are bringing in information, sensory information, into your brain so that you can process it further. And so here we'll kind of break down each type of sensory memory. For the visual system, typically, in a cognitive course, sensory memory is known as iconic memory, which that's not too hard to remember, I don't think. When I think of icon, I think of something that you can see. It's a picture. That's what an icon basically means. It's a picture, something you can see, which of course, visual icons are something you can see. So that's visual sensory memory. And the idea is that it has very short persistence, meaning that sensory memory in the visual system is thought to be really quick, like on order of like milliseconds, very quick, definitely less than a second. That information enters your eyes, is quickly maintained in sensory memory. And if you don't, become consciously aware of some sensory signal, if you don't actually pay attention to it, then that sensory information decays very quickly. So kind of a key aspect of this is that um, stuff will be decay out of sensory memory very quickly unless you pay attention to it, in which case that information can then be sent to short-term memory, where you can become conscious of that information and it can be maintained through rehearsal for a longer amount of time. So visual, that is iconic sensory memory, thought to have really short persistence. And you basically, what that means is you lose the information unless you pay attention to it, in which case that information goes to short-term memory and you can maintain it for a longer period of time. Contrasting visual or iconic sensory memory with auditory echoic memory. So once again, this is, I think, kind of easy to remember because we only have echoes in the auditory system. Well, that's how when we usually think about the idea of echo, I think of going to those caves, Mammoth Cave in Tennessee when I was a kid, really big place, and you could, say echo and then you would hear your voice echo back many times. Obviously, that's an auditory phenomenon, echoic memory. And so the general idea here is that the length of persistence in echoic memory is longer than it is in visual. So the book suggests that the duration of echoic memory is like 9 to 10 seconds. So in visual iconic memory, information stays there for just a few milliseconds, very, very brief. But in echoic memory, as kind of is suggested by its name, the information kind of echoes, it kind of reverberates around up in your mind for a while, which allows you to which allows the information to kind of stay up there. Even if you're not necessarily paying attention to the information, it can kind of stay up there for a while. It will eventually decay, in theory. But you kind of have longer, if the information is kind of up there echoing around and you're paying attention to something else, you don't have to immediately pay attention to that information in your echoic memory in order to maintain it. You can kind of continue paying attention to the things out here for a little bit. That information will still kind of be reverberating around, and then you can pay attention to it later and it should still be there. And then you can start rehearsing it to maintain that information, keep it there for a long period of time. So the length of persistence is longer in echoic memory. That means basically stuff in echoic memory, sounds decay more slowly. They decay very quickly in iconic visual sensory memory. They decay much more slowly in auditory echoic memory. Okay, so yeah, here is a cool behavioral task. The cool behavioral task, the Cowan task. And if you've taken my 625, you've probably seen this demonstration, but we'll do it anyway. And I think I'll just have you guys type in your answers to the chat here in a second. So what I'm going to do is I'm going to say a long list. I'm going to perform the Cowan task. And the Cowan task, by the way, is a measure of auditory echoic memory. So I'll do the task and then we'll kind of reflect on why is this task a measure of echoic memory. So what I'm going to do is I'm going to read off a long sequence of numbers. And the sequence of numbers is going to be so long that you're not going to be able to remember the entire thing. I think that's pretty fair to say. You will not be able to remember the entire thing. So instead, what I want you to do is repeat as many of the digits at the end of the sequence as possible. So at some point, you don't know when I'm going to stop. I'm just going to be reading off a sequence of numbers, and at some point, I'm just going to stop. And then what I want you to do is remember as many of the numbers at the end of the sequence as you possibly can, in the correct order, in the number that they were presented, in the order that they were presented. So any questions or comments about the instructions? Not seeing anything. Okay, I'll start now. Hopefully I'll be able to, I'll speak a little bit more into the microphone. Okay, so here I go. 8, 4, 6, 9, 2, 1, 3, 7, 4, 8, 6, 9, 2, 3, 4, 5, 9, 6, 8, 2, 1, 6, 3, 7, 4, 8, 1, 5, 3, 6, 9, 7, 4, 2, 1, 8, 5. So try and remember as many of those numbers at the end of the sequence as possible and go ahead and type them in. And try not to look at other people's answers. I don't want people to be cheating. You got some chats here. Let's take a look. I always remember the game One Away by The Price is Right. And that's what I feel like this is. Let's see. Yes, 42185 is correct. Let's see, 974. Yeah, wow. 9742185 by Michaela. That was 1, 2, 3. That was correct. 8469213. That is not 6974285. Yeah, that's good. Oh my goodness, yeah, that's really good. 8 numbers right there by Helen. 742185. So yeah, the people that reported their numbers did pretty well. Yeah, I'm guessing that, oh, we have another new message. Good, yeah. So the people that were reporting, there's 20 some people here today, and I definitely didn't get everyone reporting. But the people that did report actually did pretty well. On average, I would say, it's not calculated, but on average, I'd say you guys are getting about 6 numbers right, which is pretty darn good, actually. I'm guessing, though, that the people that felt most confident in their answers are the people that were reporting. The average in this task is usually about 4 numbers that people are able to get correctly. Me personally, I did this once on a trip with my wife, long trip between Las Vegas and California when I used to live out there. And we were, it's a long, boring trip. If you've ever been on that interstate, it's just all desert for like 4 hours straight. And so we were doing this for a while. And really the best I ever got was 3. So this is a hard task. My wife was able to get 4 pretty consistently, which made me mad. She clearly had a better echoic memory than I did. And so this is a task which I imagine, I don't see your expressions out there. I can't today because of we're doing Zoom, but most people, this is kind of a task which is a little bit hard. I know me personally, it was hard because you don't know when the end of the sequence is going to occur. So you have to just kind of wait. And then when the sequence ends, there's some numbers that are hopefully kind of floating around in there. And then at that point, whatever numbers are kind of echoing around, floating around in there, those are the numbers that you provide. And the more numbers you have echoing around in there, the more numbers you'll be able to provide to the researcher. But the thing that makes this hard is that because the sequence length is unpredictable and long, you don't know when to start using your attention to start, paying attention to the numbers that you're trying to remember. There's so many numbers, you don't really know which ones you're supposed to be encoding or you're supposed to be focusing in on because, your task is to remember as many of the numbers at the end as possible. And so this is why this is considered a measure of echoic memory, is because that rehearsal component, which is something that short-term memory has. Maybe we should look back at the diagram, actually. This rehearsal component is something which is in short-term memory. So like oftentimes if a person is giving you a number to remember, you kind of start rehearsing it right away if you have to remember it. But in the Cowan task, the task that I just did, it's not really easy to rehearse because you don't know what information to rehearse. I give you a long sequence of numbers and you don't know which numbers you should be trying to rehearse. And so the Cowan task kind of forces you to rely on your sensory memory because you don't know where or when to start rehearsing. And so it's harder on average. I don't know if I actually say the length. I might say it in the notes portion, but it's pretty important. The average, research, there's been several studies that have actually used this task. The average amount of numbers the participants can remember is 4 plus or minus 1. So there's a little bit of a variation there. So basically on average, participants get between 3 to 5 numbers correct. That's the average score on the Cowan task. It's hard, once again, because it relies primarily on echoic memory, and echoic memory does not allow you to use your attentional networks, particularly those in the frontal lobe, to rehearse the numbers as efficiently. So it's more of a pure measure of auditory echoic memory. Contrasting this, the Cowan task, with, actually, I want to talk about the Miller task. So I'm just going to skip that. Contrasting that with this, which is the Miller task. The Miller task is more of a measure of short-term memory. The Miller task is a measure of short-term memory because rehearsal is more possible. And in general, performance on the Miller task is better. So an example of the Miller task is in the Miller task, you are, let's see if I write it here. Your job is to repeat all of the digits in the sequence. But the thing which is important about the Miller task is that the sequence length is somewhat predictable. Usually the sequence is around 5 to 9 digits long. And you, the participants, are aware that the sequence length is somewhat small and manageable. So in theory, the Miller task, so this would be like, so the Miller task would be something like this. Remember these digits. 3, 6, 9, 7, 4, 2, 1, 8, 5. So that's a sequence of 9 numbers, the same 9 numbers that I used at the end of the running span task. But it should have been a little bit easy, should have been pretty easy to remember that all 9 of those numbers there. Because you can basically, as soon as the numbers start, you can start using rehearsal to try and maintain that information in short-term memory once again. In the Cowan task, you can't do that because you don't know when the sequence is going to end. So you don't know when to start rehearsing. You don't want to start rehearsing all of the numbers in the Cowan task because there's like 30 or 40 numbers. And all those numbers that you're rehearsing at the beginning, it's basically a waste of time because your job is to remember all that stuff at the end. In the Cowan task, you can't do rehearsal. But in the Miller task, when the sequence of numbers is somewhat manageable, like 5 to 9, you can start using rehearsal right at the beginning. And so in this Miller task, you've probably heard about this. This is this, if you've taken some intro psych classes, we'll talk about this. The magical number 7 plus or minus 2. That is based on the Miller task. It's the so-called capacity of short-term memory. But the important thing is that the Miller task, the capacity is higher than it is in the Cowan task. They're similar tasks in the sense that in both you're trying to remember sequences of digits, sequences of numbers. But in the Cowan task, people usually can only remember about 4 numbers, where in the Miller task, people can usually even me, who does not have a particularly good echoic or short-term memory, I can usually remember 7 numbers, no problem, in the Miller task. The primary difference, I think is said right here, the Cowan task prevents rehearsal, and this thing that we'll talk about in a second called chunking. These are both components of short-term memory that require your frontal lobe, your executive attention, to maintain information in short-term memory for longer than it would otherwise be maintained. Cowan task prevents that because of the end of the sequence being unpredictable. Whereas the Miller task allows you to do that, and so the Miller task performance tends to be better. So I do have a brain finding pertaining to this stuff right here. This is this is a study that's taken directly from your textbook. And this concerns auditory echoic memory. So this is kind of analogous. It's kind of similar, at least in theory, to what's going on in the Cowan task. Once again, in the Cowan task, you weren't able to use rehearsal. You just had the long sequence of numbers. When the sequence of numbers ended, you had some numbers reverberating around up there. And supposedly the way you were able to do that task is when the sequence ends, whatever numbers were echoing around in there, you were able to report them. But in the Cowan task, not easy to use rehearsal. So it's more of a pure measure of echoic memory. So the mismatch negativity, the textbook calls it the mismatch field response, but they basically mean the same thing. The mismatch field response is a brain, it's measuring either electrical or magnetic responses of the brain using usually EEG, but you can also measure it with MEG as well. But I've seen way more research using EEG, like measuring the electrical activity on the scalp rather than MEG, which measures magnetic on the scalp. But the mismatch negativity is a response. It is a negative deflection in the brain's response that occurs in response to a so-called deviant stimulus. So I need to explain what the standard and deviant stimulus are. So in the mismatch negativity paradigm, you're actually not told to remember anything. In fact, oftentimes in the mismatch negativity paradigm, they'll actually have you watching a silent movie. You're listening to sounds in headphones, but they actually tell you you don't even have to pay attention to those sounds. There's a silent movie, you can just watch that. But the researchers really are interested in your brain's responses to those sounds, even though you're not paying attention to them at all, which is okay, because if you remember, auditory echoic memory, that's processes in your mind and your brain that are occurring even if you're not paying attention to the sounds at all. It's just kind of the taking in of the auditory information, even if you're not paying attention to it. And so in theory, you should be able to measure auditory echoic memory of sounds, even when a person is not paying attention to those sounds at all, even if they're watching, a silent movie on a computer. So the nature of those sounds is that some of them are so-called standard sounds, and a rare occurrence will be what's known as a deviant. So the standard sound is one which is repeated over and over again. So as a participant, being in the mismatch negativity paradigm is usually kind of boring because you're just going to hear sounds repeated over and over and over again. So it would be something like sometimes it's pitches, so it'll be like the same sound pitch over and over and over again. Or maybe it would be like a speech sound. That's the example that I'll give today. So I might do a mismatch negativity study where the standard would be the syllable da. And so I would say da, 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 da. That's the standard. And it's the standard because I repeat it over and over. And then occasionally there will be a so-called deviant stimulus, which is the stimulus which is different than the standard. So my deviant stimulus I will have be ba. So an example of a trial of the mismatch negativity would be something like da, 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 ba, da. And then you go on for da for a while more. And then, 1 out of every 10 or 1 out of every 20 sounds will be the deviant, the ba. And once again, I'll remind you that in the mismatch negativity paradigm, you're not usually paying attention to the sounds. It's a pre-attentive phenomena. You're paying attention to something else, but your brain is still responding to those sounds. And what's interesting is even though you're not paying attention to those sounds, your brain responds differently to the deviant sound compared to the standard. And so you can see those differences. We'll just focus in on one of these for now. We'll just focus in on this one right here. And the blue trace is the brain's response to the deviant sound, so ba, whereas the standard, the red trace, is your brain's response to the da sound, the one that I repeated over and over again. And you can see that there's a difference in these waves. So in this, they don't actually show like the polarity here, but blue is more negative than the red. So positive is up, negative is down here. The response of the deviant stimulus in the brain is the polarity is more negative compared to the standard. And that's why, by the way, it's called the mismatch negativity. The deviant sound mismatches relative to the standard. There's a difference, a clashing. Your mind is kind of expecting da over and over again, but occasionally there'll be a deviant sound. That deviant sound mismatches. It does not go with the standard. They clash. And when your brain, or your echoic memory to be more precise, detects this clashing, detects this mismatch, it results in the brain's response being more negative than it otherwise would be. So the brain's response to the deviant is relatively more negative than the brain's response to the standard. So in theory, the thing which causes this mismatch response is that when you hear the standard over and over and over again, basically you're having like an accumulation of information regarding that standard in your echoic memory. It's as though, the more times you hear that standard, like you get this memory trace of the sound da, the standard, in your echoic memory. And it's kind of being stored there for a while. Remember, echoic memory can be stored, in theory, for a while, several seconds at least. And then, each time that da sound occurs, it's like, it fits just nicely with whatever that is in your echoic memory. Da is being stored there. Then you hear da again, and there's no mismatch. They match perfectly. And so the brain's like, we're all good. We're all good. Every time it hears da, the da sound is matching with what is being stored in echoic memory. However, when there is those occasional deviants, the mismatch is supposedly detected by your mind, by your brain, by your echoic memory, because the thing which is echoing around in your memory, in your echoic memory, is da. But then you hear ba, and then there's a mismatch. The thing which is entering your echoic memory is different than what is currently being represented in your echoic memory. And your brain detects that mismatch. And the mismatch in theory is occurring in your echoic memory. There's all these different components of memory, but the mismatch negativity, according to a good amount of researchers, this mismatch is thought to rely on echoic memory, those parts of the auditory system which do not require attention. So the most complex aspect of this study, which the book also discusses, has to do with the inner stimulus intervals. And it is complex, but I think it's interesting and kind of important. And so I want to talk about it because this is one of the ways that the duration of auditory echoic memory has been approximated. So what these numbers here are, where it says inner stimulus interval, these are the amount of times that separate each standard and deviant stimulus. So 0.75 means that there is basically a stimulus that occurs, whether a standard or deviant, every 3/4 of a second. So that's pretty regular. Da, da, da. That's probably around every 0.75 seconds. This is a stimulus every 1.5, every 3 seconds. So this one right here would be like da, da. And then moving on to like 12 seconds. I'm not going to do an impersonation here because it would just take too long, but I would say a da sound, you would wait 12 seconds. And then there would be another sound. It would either be, another da, or it might be a deviant sound, a ba. And remember that in theory, the way the mismatch negativity is being produced is when the representation in echoic memory clashes with the information which is coming in to echoic memory. But also remember that echoic memory, that thing which is reverberating around in there, that representation is thought to always be decaying with time. And so if you have enough, there will be a representation there, but if you're waiting like 12 seconds, we'll say, basically that representation in echoic memory starts to decay, and that when a deviant sound occurs, it goes into echoic memory, but there's no representation in echoic memory with which it can clash. And actually that can be seen right here. So if you look at the long interstimulus interval right here of 12 seconds, this is supposedly when that representation in echoic memory is basically decayed because it's so long. You can see that there's virtually no mismatch negativity response. The blue and the red waves are almost completely on top of each other. There's a little bit of separation there. There is, but it's very, very small, especially when you compare it to up here. And you can kind of see the trend for the short interstimulus intervals. There's relatively big separation between the red and blue lines. But as the interstimulus interval increases, the amount of separation definitely decreases. Supposedly, the reason why there's a decrease in the separation of the red and blue lines is because that information in auditory echoic memory is decaying. When that information is decaying, that means that when there's a deviant stimulus, the ba sound, it's going into the echoic memory, but it's not clashing with anything anymore because the stuff that had been in echoic memory has decayed. The da sound that was there, if the interstimulus interval is long enough, will decay. So when the deviant sound goes into echoic memory, there's nothing to clash with, which means the mismatch negativity response will not be produced, such as these particularly occurs with these long interstimulus intervals. In general, the longer the interstimulus interval, the smaller the mismatch negativity response to the deviant will be. Let's see. Okay, so we'll talk a little bit about short-term memory here, and then we will call it a day after this. So we will not get to long-term memory today, I don't believe. So now we're moving to short-term memory, which is, once again, that second component in the model I showed you at the beginning of class. One of the key features of short-term memory is it does have this self-referential rehearsal loop, which allows information to be stored or maintained in short-term memory for longer than it otherwise would be. So yeah, I guess we'll be talking here a little bit about the different types of short-term memory. And the main different types is spatial short-term memory, which is requiring you to remember where in space different things are. So they'll be like, usually the way this works in an experiment is you'll be looking at a computer and there'll be like different objects which appear on the screen, and they, you'll see them for a little bit and then they'll go away, and you have to remember where those objects were. And then there'll be some delay period, and then you have to, after at some point the computer will say, okay, now push press on the screen where those objects occur, and you have to push the right spots on the screen where the objects had just appeared. And they'll measure your brain activity during that delay interval. Once again, you see the stuff on the screen, then it disappears, and you have to remember that stuff for a while. And then they'll say, okay, go. And you have to touch the points on the screen where that stuff had just been. They're measuring your brain activity during that delay interval while you're waiting for them to say, okay, go. So that's a spatial short-term memory. And then there's also a digit memory, which I've already kind of given you an example. The Miller task is an example of digit memory. They'll just give you a sequence of digits, usually like 7 or 5 to 9 digits long, and you have to remember the entire sequence of numbers. So those are the two types of short-term memory, kind of a visual, spatial memory versus an auditory or verbal or digit memory. And regarding the brain, there's actually been, another topic related to hemispheric asymmetry in this class is that the findings regarding hemispheric asymmetry, hemispheric differences for spatial versus verbal, that is visual versus auditory, short-term memory are pretty strong. There's a whole lot of evidence, and I'll show you some of the evidence, I believe, on the next slide, that the right hemisphere of the brain is more important when you're remembering the spatial arrangements of things. When you're doing spatial short-term memory, a lot of activity in the right hemisphere of the brain. And we also talked about way back at the beginning of class, at the beginning of the semester, there were some of the first lesion research that had been performed with people that had lesions of the right hemisphere of their brain who also had impairments remembering with spatial short-term memory. I think I have a question here. Let's take a look. In the digit memory, is the digit memory better for left-handed people in the right hemisphere also, or have the studies only been focused on right-handed people? That's a good question. And my understanding, so most of the research definitely has been on right-handed people. In fact, when I did my dissertation on hemispheric differences, I actually only analyzed the data of the right hemisphere, the right-handed people, but I also only had like 150 participants. I only had like 5 to 10 were actually left-handed. So the sample size, the problem is the sample size of left-handed people tends to be small, and definitely smaller than right-handed people. And so there's not as much research on left-handed people. But my understanding of this is, yes, left-handed people do have significantly different patterns of asymmetry than right-handed people. So that's a really good question. Most of these patterns of asymmetry that are talked about in this class are assuming that the participant is right-handed, and left-handed people are likely to have different patterns of asymmetry. Sometimes people with left-handed will have literally the complete mirror image of asymmetry. So left-handed people are more likely, for instance, to have their spatial part of their brain be their left hemisphere and the verbal part of their brain be the right hemisphere. So sometimes in left-handed people, the hemispheres are completely switched, and that's more likely to occur in left-handed people than right-handed people. So really good question. I hope I answered it well. Let's go ahead. I'll come back to this slide, I think. I'll just show you this stuff right here. So this S stands for spatial, and the W stands for working memory. So working memory is not exactly the same as short-term memory. In fact, the difference is pretty important, especially in a cognitive psychology class. I'm not going to actually require us to know the difference in this class between working memory and short-term memory. But I took these are kind of similar, I believe. I took these from an article. I think it says the article in the notes. There's similar figures. I found these images and I realized they were similar in the 5th edition. There were similar images in your textbook, but I kept these in there just because they're taken from an actual article. Basically they're showing the different regions of the brain that are activated depending on whether people are performing a spatial memory task. So they call it spatial working memory. You can kind of think of it for a cognitive neuroscience class. You can also think of this as spatial short-term memory compared to those regions of the brain that are activated performing a verbal working memory or verbal short-term memory task. And so what's shown here, all I really care about is the adults. There are slight differences. These are children over here. And really the differences between the children and the adults are relatively minor. So we'll just focus in on the adults. So these are up here, these are regions of the brain that were more activated when people were performing the spatial short-term memory or working memory task compared to the verbal working memory task. And you can see there's a lot of activation here in the right hemisphere of the brain compared to the left. There's a little bit of activation here in the left hemisphere, no doubt about it, but there's quite clearly more activation in the right hemisphere. And you can see that's the occipital lobe, a lot of activation, the parietal lobe, a lot of activation. Those are the two main lobes. Really, there doesn't seem to be, there's a little bit going on in the temporal lobe, but most of it's occipital and parietal lobe, apparently. And then this is kind of on the boundary. I don't know if you would consider this frontal lobe or parietal lobe. It's too close to call in this image. Clearly, a lot of right hemisphere activity when people are performing the spatial task. Down here, these are the regions of the brain that were more activated when people were performing a verbal working memory task compared to a spatial working memory task. Here's the left hemisphere of the brain. And here, what's interesting is, there's clearly a left, this is a thing which is more strong in the left hemisphere of the brain. It's also kind of interesting for the verbal working memory task, there's a good amount of frontal lobe activity and temporal lobe activity, not as much occipital and parietal. Nevertheless, this is a left hemisphere thing. It's more dominant in the left hemisphere, verbal working memory, compared to the spatial working memory, which is relatively more in the right hemisphere. So we'll go back to this slide. So those are the various neuroimaging. That was the neuroimaging study that I just showed you, with those slides for, with the activations in the brain. But there's also a dichotic listening study. Actually, there's several. There's a lot of evidence from both of these paradigms. Neuroimaging, a lot of evidence supports this distinction between the left and right hemispheres. And then there's also good evidence supporting this idea that verbal working memory relies more on the left hemisphere than the right, coming from dichotic listening, which is a purely behavioral method. So what I like about dichotic listening is it doesn't require a very expensive fMRI machine. fMRIs cost thousands of dollars just to run one participant for an hour. Very expensive. Dichotic listening you can do for basically free using software, which is available on the internet now. It's very easy to do a dichotic listening study, and they support a lot of the findings that you get regarding neuroimaging, at least as far as hemispheric dominance is concerned. And so dichotic listening studies, once again, use this idea, this assumption that information which is going to your right ear is primarily processed by the left hemisphere of the brain, and information that goes to your left ear is primarily processed by the right hemisphere of the brain. Another thing about dichotic listening, the term di refers to two sounds. So two sounds is basically what that means, being presented to you simultaneously. So in dichotic listening, there's always every time you hear a sound, there's always one sound being presented in one ear and a different sound being presented in the other. So you're listening to two different things, one thing in one ear, a different thing in the other. And usually the way this works, and I'll show you a slide here in a second, is your job as the participant, you're hearing numbers in your ears. Your job is to remember as many of those numbers in your ears as possible. And it turns out that when people are recalling the numbers, they're much more likely to recall the numbers that were presented to their right ear than their left. And remember, the right ear is thought to be primarily connected to the left hemisphere. And so the fact that you are more likely to recall numbers which are presented to your right ear suggests that the left hemisphere of the brain is more important for paying attention to those numbers and encoding them in short-term memory. So let's look up more at this. So this is actually an actual study. I wonder if I have the citation down there. Well, I may or may not have the citation in the notes portion. I actually don't remember if I ended up writing it. But this is definitely a published study that has used this exact dichotic listening task on short-term memory, verbal short-term memory. And so this is like the key part right here. These are, a visual representation, but it's dichotic listening. So these are what these numbers are. These are the number pairs that are presented. So this 1 would be in like the left ear, and it would occur simultaneously with the 5. So you'd hear 1 and 5 at the same time. And then a second later, then you would hear 2 and 9. And right here, this would be an example out of all this data down here. This would be an example of 2-digit pairs. 2-digit pairs. That's pair number 1, and this is pair number 2. Your job as the participants, you actually heard 4 total numbers here. 2 of them were in your left ear. 2 of them were in your right. Your job as the participant is to respond with all of the numbers that you possibly can. So the correct answers are 1, 5, 2, and 9. However, it turns out that when people do this task, they're much more likely to report the 5 and the 9, and they're more likely to omit the 1 and the 2. The numbers that they're more likely to hear are those presented to the right ear. They're less likely to present those that are presented to the left ear. And to kind of demonstrate that, the data are down here. And you have to, so the mean percentage of numbers correctly reported. So there's several variables here. Looks like there's, 2 different variables here. So these are the digit pairs. So these are the amount of pairs that you have. So on these trials right here, where there's only 1 pair, there's 1 number presented to your left, 1 number presented to your right ear. Only two total numbers. These are actually really easy. So people get 99.4% of the numbers in those types of trials presented to the right ear. So almost at ceiling. When there's only 1 pair of numbers, 1 in the left, 1 in the right, you're almost getting 100% of the numbers presented to the right ear correct, which is about the same amount of numbers that you get presented to the left ear. So really right here, there's not a whole lot of evidence of ear asymmetry or hemispheric asymmetry because the accuracies are not significantly different, but that's only when there's 1-digit pair. The real interesting stuff happens when there's more digit pairs. So once again, 2-digit pairs, which is the example here, there's 2 digit pairs, digit pair 1, digit pair 2. Then you start to see evidence of an asymmetry. So here, when there's 2-digit pairs, people got 95.8% of the numbers in their right ear, but only 92.9% of the numbers in their left ear. So now we're getting a bigger difference in accuracy. It's about a 3% difference in accuracy where people are doing better at recalling those numbers in the right ear. But the strongest evidence by far, I would say, comes from the trials in which there was 3-digit pairs. So this would, digit pair 1, digit pair 2, and then there'd be another digit pair 3. So you have your 100% correct answer would require you to get all 6 of the digits right, all 3 in the left ear, all 3 in the right. But when you do this, these are clearly harder trials to get all of the numbers right. People are only getting 82% of the numbers in their right ear correct on these trials. But even more profound, they're only getting 71.6% of the numbers in their left ear. So that's like a 10% difference favoring the right ear. So in general, you can see across all these trials, it's quite clear that the numbers that are presented to the right ear are more likely to be correctly reported than the numbers that are presented to the left ear. So given the assumption that the right ear is connected to the left hemisphere, this suggests that the left hemisphere of the brain is more important for verbal short-term memory, which corresponds quite nicely to these findings right here, which also suggest, these are neuroimaging studies that suggest that when you're remembering a sequence of numbers, that relies more strongly on the left hemisphere of the brain than the right. I think we'll call it a day there. We have a little bit more on short-term memory to get to next time, but we'll call it a day there anyway. So I'll stop recording now.